Okay, I'm very happy to welcome Professor Po-Shen Loh from Carnegie Mellon University as our guest speaker today. He's been a friend of New York Math Circle for many years, and he's going to talk to us about the research that he's been doing related to COVID-19. I won't go into his list of accomplishments because then I would take up all of his time for his talk. And so without further ado, I'd like to hand off to Professor Po. And please welcome him to New York Math Circle again.
Great. Well, thank you very much. It's a real pleasure to be able to talk to everybody. I will say New York Math Circle is one of the first places that I started going to regularly as I went to give math talks around the country. Goodness gracious, I don't know how many years it's been since the first New York Math Circle talk that I gave. But I remember that your community is wonderful. I was always very impressed by how thoughtful people were, how interested people were in thinking about math, and basically how people thought that math was beautiful. And I was really also impressed by the staff and the other teachers who are at New York Math Circle. I just want to say, to all of the students and parents who might be watching, you guys are really lucky to have people who are that passionate about math and education to work with you so regularly. And I'm very, very happy to be able to work with them too. So now you know me, a lot of people in this community know me as the guy who does math and math education. And I guess I give talks around the country about random fun topics in math. And that's indeed what I normally do, except that, as you know, the world changed very suddenly in the beginning of this year. So as a bit of introduction, I'm a math professor at Carnegie Mellon. I also happen to be the national coach of the US International Math Olympiad team. And none of this has anything to do with COVID. But in the middle of March, actually on Pi Day, March 14th, 2020, something happened. It was Pi Day. But what else happened is that I got a message because I happen to be a member of a group called the Hertz Foundation Fellows. The Hertz Foundation is an organization which goes and finds about 15 people every year who are about to start their PhDs. And then it provides them with a free PhD in exchange for making a moral commitment that if there's ever a moment of national emergency, you'll come to help. And I'm actually one of these people. This group was started actually by somebody who knew someone who was involved in the Manhattan Project. This is where a lot of scientists got together to try to win World War II. And at the height of the Cold War, we weren't sure as a country whether we would need a second Manhattan Project. And so there was an organization called the Hertz Foundation, which went and tried to find people who could potentially come together to be the second Manhattan Project if need be. And we never thought that we'd really need to come together to build a bomb. And when I'm one of these people, when I signed on to this, I thought, I believe in this mission to come to help if there's a national emergency. I don't really know how it'll be useful. I'm a mathematician. But now what ended up happening is in the middle of March, we got activated. And we got activated because COVID-19 is a national emergency. When I got activated, I didn't know what I could do. Actually, I'm a math person. And I saw the people next to me. You got these biologists who are working on some incredible ideas of making vaccines or treatments. Over here, you got mechanical engineers who are finding interesting ways to make ventilators more efficient. And I'm a math guy. What can we do? Well, it turns out that I didn't know what I could do until the second day. I was thinking about this. And the second day, I happened to be reading the thesis of my PhD student. When you write a PhD, you have to write a thesis, some long sequence of papers, actually. And I was reading this, and at the second sentence, it hit me like a flash. COVID-19 is actually a network theory problem. We're in New York Math Circle, so I'm going to call it a graph theory problem. COVID-19 is a graph theory problem. And actually, we can use graph theory to try to stop this. So I realized this, and then I threw everything down, and I said, I think I'm just going to try to stop COVID-19 now by using graph theory and mathematics. And today's talk is going to talk a little bit about how, using math, you can go and try to attack the problem called COVID-19. Actually, since putting that down, I have to apologize. I didn't actually read the rest of my PhD student's thesis. Fortunately, he's a super genius, and he didn't need me to read his thesis. He graduated anyway. So no PhD students were harmed in this process. But now I'm going to talk a little bit about what you could do with math to try to stop the COVID-19. Okay, so the first thing I'm going to do is I'm going to maybe write a bit of stuff on my board. So this is my board, and just a second, just pulling this around. I want to write a few things of why you might think of using math to try to fight COVID-19. So the first thing is many people have heard of this idea of R0. Just checking my tablet, this is good. So R0. And some of you may have seen some segments of this talk before. I will tell you there will be some new stuff in here that's not in the previous things. So R0 is somehow a measure of if somebody is infected with COVID-19, how many more people are they going to infect? So this is somehow measuring, it's an estimate the number of people that get infected by well, let's say an infected person. Okay, so now the idea is that there might be somebody who got infected, and now how many more people are they going to infect? The idea of exponential growth is if this R0 is bigger than 1, then your infection balloons out of control. Because then it's like if there's someone who's infected, they infect more than one other person. Each of those infects more than one other person, and then more than one, and it blows up. So the problem is if R0 is bigger than 1, it's a problem. So R0 bigger than 1 is an explosion. Okay, and this is what you may have read about in the news, that somehow people are trying to find out what is this R0, is it bigger than 1? And it was actually estimated to be somewhere around 2 or 3. It was something like 2.5 or 3, or there might even be people here, well, not might be, there are probably people here who are from families where maybe some of your family members think about this, and they know more than I do. But I'll look at it from the math side. And I'll say that, you know, it was estimated R0 was like somehow 2 to 3. And it might even be 4, it might have been 2.5, but it was somehow more than 1, and it was somewhere 2 to 3. Now, that's bad because that means that the virus spreads to lots of people. But there was something else which is really important. The other piece that was also important was that this virus spreads before you feel that you're sick. That's pre-symptomatic transmission. It also has what's called asymptomatic transmission sometimes, which is also bad. It's that you don't even show any sign of being sick, but you're transmitting. But there was a very interesting paper that I'd seen, which showed just how bad of a problem this pre-symptomatic transmission was. It was a chart. And that chart looked something like this. Here's an axis. This axis is days after symptoms. And this chart obviously has a 0. That's when you have that's the moment that the symptoms start. And the chart looks something like this. It's not quite drawn to scale, but the key part of it is. And what this is here is this is somehow the amount of virus being transmitted. So this green thing here, somehow it's what we call the viral shed. And the interesting thing is that this was -2. So how do we interpret a graph like this? The way you interpret a graph like this is that here's the days after symptoms, here's 0, days after symptoms, and here's how much virus you're spreading. And this is supposed to be a distribution. It's called a distribution. It's like how much of the virus is shed at the various times. And this was the graph for COVID. Do you see something bad about this graph? The thing that's bad about this graph is the -2. If you compare this to SARS-1, the same research paper for SARS-1, the graph started here and then it went up. So for a lot of other diseases, it is after you start coughing that you cough on people, and those coughs make people sick. In fact, even the notion of coughing or sneezing on someone is what gets people sick. That's what we're used to. That's what humans are used to, that we spread disease only after you have a cough. What's this? This is crazy. What this is saying is that 2 days before symptoms even start, just by talking to people, then the particles that come out of your mouth go into the other person. And there was a great explanation of this in an article I read actually just last night. It was that, I don't know if any of you have ever experienced this, but sometimes if somebody ate like a garlic bagel or like an onion bagel, or I'm talking about garlic breath or onion breath, Has anyone ever smelled someone else's onion breath or garlic breath? Presumably, yes. It's when the person gets close to you, right? Now think about it this way. If you can smell their onion breath or their garlic breath, you also can get their COVID. Does this make sense? What I'm trying to say is that the fact that you have detected some particles that came from their, I guess, their body, means that if those particles were COVID, you could have got that too. And that's the problem. COVID starts to spread out here before you're actually coughing. And that's why it became a big deal, because look at how much of this graph is here. This is insane. Actually, when you look at this, what's relevant, again, my thing's not completely to scale, but that article that I was referring to, the article is in a journal called Nature Medicine. Nature, by the way, is an extremely legitimate journal for science. But over here, it was estimated about 44% of the total. I'm just showing how you could use math to start to think about what we need to do to fight COVID, right? So if you look at this, now let's start putting this together. First of all, 44% is huge. If it was that it starts spreading before you're coughing, but you need to have a real cough to go and unload the virus onto other people, well then, you could still use the method of, oh, they've started coughing, so they shouldn't go to school, they shouldn't go to work. But this is invisible, and this is huge, 44%. Now I'm gonna do some multiplication. Let's suppose R naught was like 2.5, okay? And this is where I'm saying this is not my specialty. My specialty is the mathematics part. The biologists, the medical experts are supposed to figure out what this actually is. So over here, I'm going to put a double question mark because nobody actually really knows what that is. But I'm just going to say, let's use this for the sake of argument because it's probably not far off, okay? I see that people, by the way, are saying about people refusing to wear a mask because they don't think they're sick. I'm about to get to that, right? So now suppose it's 2.5, suppose, and it might even be 3, but suppose it's 2.5, and suppose 44% of that is before you know you're sick. Now, let's go to your comment about mask. What if we live in a world where everyone, as soon as they feel sick, wears a mask? Suppose that we are able to make it so the moment you feel sick, there's no more transmission. Are we done? Because some people say, hey, maybe we should just make it so that if you feel sick, you stay at home, right? Is that enough to control this virus? Because that's how we control things like the flu. The flu, by the way, doesn't have a 44% of its spreading before you start feeling like you have the flu. So what if we just had a perfect system, not perfect, let's just do something simple where all we do is the moment you feel sick, stop transmitting. Are we done? Well, no, because let's start multiplying. 44% times 2.5. I'm emphasizing that what you need to do is if you're going to infect this many people, 2.5 people, over the course of this hump, if 44% of that gets infected before the symptoms, now this is math that I can't do, this is calculation. But what I want to write down here is then what's the pre-symptomatic? I'm going to call R0 in quotes because I'm not a professional epidemiologist, I'm just a mathematician. And so I don't want to call that the real R naught, but I mean, for the sake of this math talk that I'm giving, I'm saying, what about if we just made it so that this part, no more transmission because they get locked at home with no one else, solitary confinement? Well, out of the 2.5 people that you get over this whole thing, 44% of them go and still infect. What's 0.44 times 2.5? This I can't do, it's calculation. So 0.44 times 2.5, actually I can do that. Maybe I can do that. The trick I'm going to use, maybe. Actually, this is hard. So if I wanted to do that, yeah. So the way I'm looking at this is 4 times 2.5 is 9. Is that right? No, it's 10. It's 10. Yes, it's 10. So it's 1.1. Actually, this is a nice number. Oh yeah, actually I should have known this. Of course I should have known this. Multiplying 25 by 4 is 100, right? So 2.5 times a 4 happens to already be 10. That's easy. So it's 10 times 0.11, it's 1.1. Oh, look at that. It's bigger than 0. What does it mean? It means that if you even if you could perfectly control what happens after symptoms, you would still have an explosion. So what this is showing is that you need to have some way to deal with the pre-symptomatic. Isn't it supposed to be bigger than 1? Well, It's supposed to be less than 1 if we want to control COVID, right? But what the problem is that if this part can already make it bigger than 1, then it shows that we got to do something about this part, right? So this is a bad situation. It's a bad situation that it's bigger than 0. Oh, sorry, whoa, bigger than 1. Yikes, that's a typo. That's what you mean. Bigger than 1. Ouch. Thank you, everyone. Yes, I want bigger than 1. I totally get what you say. Bigger than 1 is what we care about. Bigger than 0 is not a problem. If the R0 was 0.7, it's okay. It's going to be a decay. From your point of view, it's this way. It'll be a decay, right? Okay. So now this is how I came to think that we need to do something to try to stop this pre-symptomatic spread. But here's something else that's kind of a fun angle to look at this. Fun not being fun because it's actually not fun. It's interesting, mathematically interesting. Sorry, fun is the wrong word in this context. But what is R0 anyway? Actually, there shouldn't be an R0. It should depend on the network. It should depend on the graph. You see, because what if I had a very strange society? Let's imagine that I have a strange society. Suppose that in this very strange society, I have people, each of these is a person, and these people are extremely, well, they're not antisocial, actually. They're just weirdly social, in that they only will ever spend time with people who are directly next to them. So this is a strange society where the only people who ever talk to each other are the ones that are next to them. So they're sort of introverts, although true introverts might actually just never talk to anyone. But these people are like on a line, and that's just how they live. And the only people they talk to ever or associate with ever are the ones who are next to them. Okay. Now suppose in this strange society, which, let's pretend it exists just for the sake of argument. In this strange society, let's pretend that COVID shows up and infects this person. How is it going to spread? Well, actually, COVID is not going to spread exponentially. You see, remember, we were talking about R0. What's this R0? I'm actually now making us look a little bit deeper. What is R0 anyway? Is there such a thing as really an R0? Not really. You have to take this graph, this network into account. All right, I'm going to use the word graph so much that I'm just going to write it down here. When I say the word graph, because I slip, that's equal to network. I'm actually a graph theorist. That's the area of research that I work on, okay? And this is called a graph. It's just that there are a bunch of people, and the only interactions they ever have are in this particular straight line. Well, now, at this point, how many people can be expected to be sickened? Yes, R0 is how many people can be expected to be sickened, assuming no immunity. But what I'm saying is that if you actually had the people laid out in this way, the growth of the disease will not be exponential. Exponential means that if right now I have 50 people with it, then after some time I have 100 people with it. And then after the same amount of time, I have 200 people with it. And after the same amount of time, I have 400 people with it. But it's not exponential. This one is linear. Everyone will still be infected eventually, we could say, except that the amount of time it takes for it to spread is very slow. Why? It's because the way that the virus spreads is not like the movies. In the zombie movies, it's like you touch the person and they immediately become infectious. Although actually at that point, it's still linear because it takes time to touch. What I'm saying is this person's sick, a few days later, that person's sick. A few days later, that person's sick. A few days later, that person's sick, and so on. So this network structure is actually really important. Now, the way society was before, I'm actually now talking about social distancing. The way that society was before was not like this. The way society was like before was there was a lot of interconnectivity. So isn't the rate decreasing? So what I'm saying is if you have a growth which is linear like this, then it won't be exponential because the amount of time it takes for 5 people to be infected to change to 6 people to be infected is like the amount of time it takes to infect that next person. And then that's the same amount of time as to go from 6 to 7. So that rate is decreasing. But that's in this very special case where we have this strange society. There's another case, which is like maybe more normal society. which is like more connected. Now what happens is you have people who, I'm not going to draw the people with their heads anymore, but I'm just trying to say you could have all kinds of strange connections going on. In a graph, you are allowed to have these lines cross each other, right? It could be like multiple connections. You understand my point. I'm just saying somehow I've got all of these people who are interconnected with each other. I could have something like this. And it's when you have something like this that you actually start to spread more. And so this R0, but the first thing I wanted to say about this R0 is that the R0 is really in the context of what is the structure of that graph you're talking about. And that's also why if you look at some of these online websites, they'll tell you what's the R of these various states. And effectively, I think what they're measuring is a combination of what the graph looks like, as well as a combination of how much protection people are taking to stop from making the spread. For example, if both people are wearing masks, the chance of having a spread is lower. Okay, so I see some questions already. I'm going to try to answer them. You'll see me walk towards the camera whenever I'm trying to read. It's like somehow, how could you really measure R0 without the necessary control? Wouldn't there simply be too many variables or unknowns in real life? Yes, and I think that's why the way people are doing this, we're estimating, right? And so if you measure R0 on a population, we don't really have a great way to model it based on just the structure of the network. We don't even know what's the structure of the network, right? And so it's not accurately known. R0 is not accurately known, but we have some rough guess of what it is. But when you look at the network, then it makes you realize that actually maybe we should use the network in some way. And so now let me start talking about what we actually do. So I make an app. I lead a team that makes an app. The app is called Novid. Novid is spelled N-O-V-I-D because it's for no COVID, right? That's the goal that we have. And what we do is we have two things where we use math to make two very big steps beyond what most people are doing in app-based contact tracing. And what we're trying to do right now is we're trying to let more people in the world know about this and know about these two flips that we're doing, two important things that we're doing with math, because we actually don't see anything else that is available in the entire world right now, which we could use to turn around the spread of COVID in the US right now. Now let me tell you about this. The first thing I'll have to show you is a video. So now you also can see I do all my stuff like on this laptop. I'm just drawing on this thing and then screencasting it at the same time. But let me go to, it's not a video of it's not like a video to watch. It's an animation. And this is actually now this is the first major feature that we've put into Novid, which is making a difference. So what you see here is you see a chart. I try to differentiate between the word graph and chart. And that's because to me, a graph is the network. But this is a chart. A chart is a visualization. What we made is we made something that shows to anybody who's in the Novid network how far away COVID is from them. Now, you may have heard of something called contact tracing. Contact tracing, I'll talk more about soon, but that's what a lot of people all over the news have been talking about as a way of trying to stop the spread of COVID-19. What I'm about to show you is flipping the idea of contact tracing on its head. So we want to show everybody this graph, this chart. And on this chart, the height of every bar is how many positive COVID cases there are. This thing here says June 3rd. And I don't know if you guys can read this, but this says U, this says first, this says second, this says third, fourth, and so on, all the way out to 12th. And over here, if you look on the bottom, it says degree of connection. Does anyone have any ideas of what this chart might mean? I'll show you things soon. So it's like, what would it mean? What does second degree of connection mean anyway? Well, it's easier for me to do that on this diagram. Let's suppose that you are this green person here. If this is you, let me now start to label a friend of a friend. You're absolutely right. So let me now start to label what it means to be at each degree of connection. So these two are at degree 1, because first degree of connection. It's funny, the word degree in graph theory actually says how many things are directly adjacent to you. So it hurts me to say the word degree, but LinkedIn calls it degree. And in order to help people understand what we mean, we said it's like LinkedIn. So somehow this thing is a 1 over here, okay? Yeah, it's degrees of separation. You're absolutely right. So this notion of degrees of separation is saying how many steps along the network you need to take. By the way, this is now 2 because you have to take 2 steps to get to where you started. This is 2. This is also 2. Any more 2s? This is also 2. I'm going to try to do my best here. Do I have any 3s? I think this is a 3. I think this is a 3, and I think this is also a 3. Please correct me if I made a mistake, because I'm very liable to make those mistakes. Can't a degree 1 also be a degree 5? Yes. So that's a good question. Let me give an example, okay? Let me go and mess this up by, what should I do here? Yeah, I'm about to change a degree 3. Let me go and add 1 edge. They're called edges. Let's add 1 edge there. Now it's not a 3 anymore. Now it's actually a 1. Does this make sense? The degree of separation is the length of the shortest path that goes to you. All right? So it's always the lowest degree. And this, oh yeah, somebody asked, what's this 6 degrees of separation? Everyone's heard of 6 degrees of separation before. Not everyone. But people have said that somehow, you know, if you think of anyone in the world, like the president of Kazakhstan, then there's probably just 6 degrees of separation of people you know, who can get you to the president of Kazakhstan. Kind of funny. I wonder how that can be done. But I mean, I'll say, in my particular case, if you guys can get to me, I happened to at some point go to the International Math Olympiad when it was held in Kazakhstan. I was the deputy team leader for US. And so when I was in Kazakhstan, I got to meet some people in Kazakhstan who are, you know, at some level of administration. So in some sense, if you can get to me in 3 steps, we can probably take 2 more steps to get to the president of Kazakhstan. But I'm just giving that example, right? But so now the thing here is that the degree of separation in graph theory is just measuring how far away you are. Okay, now what's important? Actually, what's important here is if we could construct this graph where you connect people, not by what we just used of like, you know someone. What's more important is if you can connect people based on whether or not they spend time together, then that's a very interesting graph. So in fact, the most interesting graph, the graph should be of people who spend time together. And let me give a few examples. I mean, like spend enough time in order to infect each other. For example, maybe family in the same household. Let's not use family. Let's say household. Household. Or it could be something like close friends that you hang out with. So friends that you hang out with. Or it could be coworkers, etc. But I'm saying that you basically want to put these people that spend a lot of time together. Neighbor, if you actually spend a lot of time with your neighbor, that would also be an example. But there is this network. So what I'm saying is there is a network that represents all of society. This exists. And you know, there's also connections that happen in the grocery store. But I'm going to say that for the purposes of COVID-19, yes, you can catch COVID from that person, but this is actually the backbone along which it's going to spread. I'm going to see the question. I'm coming a bit closer. Is there any way to cut this, to estimate with the R0 if you happen to be taking masks into account? Well, I'm actually not going to be talking further about R0 and estimation. That's actually not where I'm primarily working. So I don't quite know the answer to your question. But there's also an example here of teacher, right? If you happen to be teaching in the same small classroom, right? So I'm just saying there's this graph here. And now let me go back to the thing I was showing. What we do is we show you on the graph of who spends time with who, we show you how far away COVID is. Now, why is that important? Well, first of all, if you look at this, you'd say COVID's not a problem. This is June 3rd, and somehow it's very, very far away from you. Look, a degree 10 connection is like my friends, fathers, co-workers, kids, friend, teacher. Do you know what I mean? It's like pretty far away, but we animate it. So we have this thing play like a hurricane satellite. So what the Novid app is doing is it's showing to anyone as the time changes, as the date changes, how the COVID gets closer to them. I'll just play it again. I'll just keep playing it in a loop so that we can emphasize what's the point of this. Let's pretend that everyone got this. What app is this? Oh, this app is called Novid. That's the app that we're working on. N-O-V-I-D, COVID with an N. And so, oh, there's a question. How do you know? We're going to get into that soon because that's also math. But I'm talking about two angles of math, right? One angle of math that I'm using here is I'm using the idea of flipping contact tracing on its head by not doing what we normally do, which I'll contrast soon, but instead also telling every healthy person how far away COVID is from them. And this is an idea from graph theory. It's that if you use graph theory to go and figure out how far away the COVID cases are, you could show the healthy person just how far away it is. What are the numbers on the top of the red bars? Those are measuring how many COVID cases. This is, by the way, just a demonstration. These aren't real data, but this is saying that you've got a lot of COVID cases. Now, by the way, what's relevant to you is not how many COVID cases are at distance 12. What's relevant to you is whether COVID cases get to you, right? This is graph theory now. And by the way, if you saw COVID get to distance 2, today I just saw on my Facebook, somebody had posted saying, my COVID degree separation just became 2. That's what somebody else posted. And they were posting that to indicate that, oh, now they are going to be careful. You see, what's the purpose of this? The purpose of this is to help anyone who wants to not get sick to be able to do something in advance. And also, if people see the red thing coming towards them, it actually will cause certain reactions. I'm a little bit curious of all the people who are watching this. What would you feel if you saw this happening? Feel free to type in the chat. What would you feel if on your Novid app you saw this happening? We got people saying they would freak out. Yikes. And you know what you'd do? You'd start wearing a mask. You'd start washing your hands 5 times. You'd start opening doors with your elbows. You'd start, whenever you see anyone else, being like, I'm going to talk to you from really, really far away. You would be very, very careful. And you know what that would do to the spread of COVID? Do you know what would happen if people started to become careful whenever COVID got close? Then it would lessen the spread. I just showed you another way now of trying to stop the spread of COVID. One way to stop the spread of COVID is whenever COVID gets close to a spot in the graph. Let's go back to the graph theory. Whenever COVID gets close to somewhere in the graph, the people start to eliminate the edges, meaning they stop spending as much time together. And oh yeah, by the way, people are saying by the time it gets to 3 or 2, isn't it possible that it could already get to you because of the incubation period and testing period? You are absolutely right. And that's exactly why what we did is we're warning people that, don't wait until it gets to 1. It's not the same as saying I'll do my homework like the hour before it's due. In this case, there's a lag in those cases getting in. So you need to go and take action before. But when you see it coming, coming was for you this way. When you see it coming, then you can start to be careful. People are asking, where can you get the app? It is free. It's on the Apple App Store, the Google Play Store. Just search for Novid, and it's free. And it's called the store, but there are free apps on the store too. But the bottom line is that when you have something like this, what we're trying to do is we're trying to let everyone start to be careful. That is actually how we're trying to stop this spread. Why don't you use psychology and put it constantly on 5 to everyone? Yes, so that you're saying let's just get everyone scared. Well, unfortunately, if you just get everyone scared all the time, after a while they get fed up and they say, I can't be careful for an entire year. And so our angle here was, hey, let's use graph theory. And let's use graph theory to let anyone know if COVID is coming close to them. And then that will cause those people who just want to protect themselves to become careful, right? So this is one way to control COVID, so that people will become more careful whenever it gets close. Why do we think this will work? The reason we think this will work is that COVID is not spreading as much as in the US in some European countries. And so we know that if people just take more careful, if they're more careful, they actually could reduce the spread of COVID. So what we're trying to do is we're trying to help people be more careful. That's the intervention. Now, let me compare that with what you have heard about. You've heard about something called contact tracing. What's contact tracing? Does anyone know? Can you summarize for me what is contact tracing? Oh, I also want to emphasize while we're getting this summary, the app is anonymous. Nobody would want to actually tell who they're hanging around with, and no one will want to say whether they're COVID positive. So the way we made our app is that when you install it, it doesn't ask you for your name, it doesn't ask you for your phone number, it doesn't ask you for your email address, it doesn't ask you to make a username, there's no password. It generates a random number that has nothing to do with your phone. It's a completely random number, and that's you. And that's on purpose. And it also doesn't use your GPS coordinates, so it can't figure out who you are. So now let's talk about contact tracing. I saw a lot of people say this. Everyone heard about this before. Contact tracing is like this. You go find somebody. Oh, that's a bad example. That's too close. You go find somebody who's positive. And the idea of contact tracing is you find the positive person, and then you go and you ask them, who did you hang around with? And you make sure that these two people kind of eliminate from the graph. You make sure that those people don't actually spend time with anyone else because they could possibly be sick. So that's the idea. You want to quarantine these people. That's the idea of contact tracing. So the way you should think of what we're doing is we're doing contact tracing from the other end. When you do contact tracing, you go from the positive ones and you just tell the people who are directly around, hey, you should quarantine. And what we're doing is we're trying to make it so that you don't only quarantine those two, but you also tell everybody else. And why is this important? So yeah, and actually people are now saying there's a problem. When you have millions infected, this thing doesn't work as well. Not that it doesn't work as well. You should do it anyway. But the problem is when so many people are infected, you might end up quarantining too many people. Because actually, the number of people that really eventually get sick is actually only a fraction of how many people get quarantined. You can see that because the R0 was 2 to 3, whereas the number of people that might get quarantined is a lot more than 2 or 3 per infected case. So we're not saying that contact tracing is bad. We think that people should do it. But some people were wondering, why aren't people installing contact tracing apps? Because there are a lot of other apps that people have made for contact tracing. Well, here's where the mathematician in me looks at the problem and tries to distill it down to a very simple statement. What does a normal contact tracing app do? A normal contact tracing app, if you install it, will tell you if you've been around somebody who's positive, right? Normal contact tracing app will tell you if you've been around somebody who's positive. That means that a normal contact tracing app, if you install it, protects others from you. Did you get that? So this is a very important thing. If you use a contact tracing app whose job is to tell you to quarantine if you have already possibly been infected, the contact tracing app's job is to protect other people from you. What I just showed you is to flip it on its head. Tell everyone how far away the cases are. That protects you from others. Does that make sense? So the difference was if you flip the incentive structure, this is where mathematicians do stuff. We think about like, what are the basic assumptions, right? You can either protect others from you, or you can protect you from others. And the incentive changes. By the way, I am not putting down normal contact tracing. We should do that too. We should cooperate with them. I'm simply saying it's good to do both. Because unfortunately, this world is not full of people who are all altruistic. Unfortunately, in this world, there are a lot of selfish instincts. And so what we thought about is, how can you do that flip of incentives to make something that people might actually want, that delivers direct value? And if you do that, you can reduce the spread. So this is one angle. How many people are in the Novid community? How many people have Novid currently? Well, right now, there are about 50,000 people all around the world who have installed it. But things are about to go explosive. And the reason they're about to go explosive is because we are currently talking to multiple universities. I have no public announcements to make yet because all those are restricted. Only those universities will announce first, and then you'll find out what's going on. But the situation right now is that I've just unveiled for you another angle on contact tracing that actually we hope that the world will start to understand. Unfortunately, something else that I'll share with you, if you do mathematics, communicating is very difficult, especially when you want to communicate something complicated, like if you flip the model, you flip the incentives, and you also can reduce the R0. But this is like, it took some math to understand this. We're trying to help the whole world understand that there's another angle to contact tracing that everyone should also do. And if you do this, you know what's going to happen? People, even in places where they don't know that COVID is a problem, will find out that COVID is a problem. And then they will just to protect themselves, take the right actions, and consequently protect everyone else too. Aha. How do we get the numbers for the app? That's a very good question. And that moves into the next part. The next part of this talk is what used to be our biggest advantage. This now, what I'm talking about, is the biggest advantage, the fact that we flipped the incentive structure. But the previous biggest advantage was that we actually can construct this graph. And so let's start talking about how we construct this graph. One other important thing, how do the red things get in? How do you know someone's positive? That one we're also working on. Right now, the way we do the red stuff is anyone can press self-report. What does that mean? I mean, anyone can press self-report, so you got to take that with a grain of salt, right? But we're also working with universities or any governments that want to work with us, that the government can anonymously confirm a report. Let me explain that just because you might be curious. This is like game theory or mathematics. Here's how it works. Right now, anyone can press the button. So we'll believe it for what it's worth. But what we have as another feature is that if you have a ticket, you can type the ticket in. It's a unique ticket, can only be used once, one-time ticket. If you type the ticket in, it's not a normal self-report, it's a confirmed report. Okay, where do you get the ticket from? You get the ticket if your health provider, if the place you live in or the university you're going to is working with us. And we'll soon get to the friends who are connected with you. That's a really interesting part, and I'll talk about that soon. But how do you get the ticket? You get the ticket if the place you're living in is able to give you these tickets because they have worked with us. And we're trying to work with everyone. If New York City Department of Health wants to work with us, we would love to. And the way it works is that the health department or the university works with us, and they have a way that they can get tickets from us. When they want tickets from us, they say, give me a ticket. They don't tell us who it's for. They just say, give me a ticket. And we say, well, you are our trusted partner. Here, have a ticket. They might say, give me 1,000 tickets. That would be bad, by the way, if there are 1,000 cases, but we'll give them 1,000 tickets. Now, when they get the tickets, they will say, all right, I just gave this person a positive test. Here, I'll give them a ticket also. By the way, at that point, we don't know who they gave the ticket to, because when they got the ticket from us, they didn't ask us they didn't tell us any information about who they were giving it to. And then here comes some ticket someone's holding, and they give it to someone. And then that person gives the ticket to us, and we say, okay, we got a positive case. But we don't actually know who the person is, and that's by design. So now let's go and talk about the other part, which is fun. And I'm sorry, I've got some questions here. Yeah, there are antibodies, there's vulnerability. Actually, what I'm going to say is that we don't understand enough about this disease. And there's something I also want to tell to all the young people who are on this call. Please don't think that the disease doesn't hurt you. I mean, one of the sad things is that young people assume that it's not going to hurt them. And if people who are, 20 or 15 say, it doesn't matter if I get it, actually, that's not true. We don't know if it hurts you long term. There are viruses that you can get that just stay in your body. Even if you fight them off, they stay in your body forever. And we don't have enough long-term information about what happens with COVID for us just to say, oh, let's let everyone get it. It won't be a big deal. What if it has something which 10 years later, it turns out to be like horrible, right? So please don't think that COVID's not a problem for you, because it might be. We just don't know. Okay, so now let me move into the other part of what we did, which was the previous big deal. The previous big deal was we actually can measure how far away these are. So I'm sorry, we can measure what these are, who is connected to who. Here's what we do. You may have heard of Bluetooth-based contact tracing apps. We don't use Bluetooth for our distance measurements. Bluetooth-based contact tracing apps work like this. There's a phone, it has Bluetooth. The Bluetooth tries to contact the other phone by Bluetooth the same way that you could connect headphones or a speaker or something. And the Bluetooth apps measure what is the strength of the signal that was received from the other one. It's like a radio signal. It's like, how strong is my signal? At first, that makes sense because there's something called the inverse square law, right? So if you have the inverse square law, and what you're measuring is you're measuring the amplitude of the signal received, well, then somehow, the strength should be inversely proportional to the square of the distance. So you can get the distance, right? Well, not really. The best analogy is like this. How do you find out how far away a thunderstorm is? Anyone want to type in? You can type it in while I go and explain. How do you find out how far away a thunderstorm is not by how bright the lightning seemed to you. The lightning brightness is the signal strength of the lightning, the light. By the way, Bluetooth is radio waves. Bluetooth is electromagnetic radiation. It's the same kind of radiation as light. So why don't you find out how far away the lightning is, how far away the thunderstorm is by the brightness of the lightning? Well, it's because you don't know about the cloud situation. You don't know about the strength of the rain that's blocking the light. You don't know about trees. You don't know about the curtains. You don't know about how big your windows are. You don't know whether you're wearing sunglasses. You don't know whether or not there's a bathroom mirror that's reflecting extra strength to you. It just doesn't work. And furthermore, you also don't know how big the lightning bolt was in the first place. Or you don't know if the lightning bolt was going your direction or the other direction. It just doesn't work. Actually, everything I've just described has analogies in the Bluetooth signal strength. In the Bluetooth signal strength, you don't know what angle the phone was pointed because that affects the antennas. The antenna direction affects the signal strength. You don't know what phone model it is. You don't know if the phone's on battery saver mode. There's like all of these things. They just don't work. So actually, if you look at the Bluetooth-based contact tracing apps, there is no Bluetooth-based contact tracing app in the world that on the app itself tells you how far away the other device was. Ours does. And that's because we use sound. Now we see all the answers. Everyone said, oh, duh, you go based on how much time it took for the sound to get to you. So what we do is we just measure the time it takes for an ultrasonic pulse. Ultrasonic just means beyond what you can hear. We've got two phones, right? One phone makes a sound to the other. And we measure the distance based on the speed of sound times the time that it took for the sound to travel. You're asking, isn't that inefficient in terms of battery? No, because we actually use both Bluetooth and ultrasound. So actually what we do with this is there are two devices, and they actually first use Bluetooth to start talking to each other. Bluetooth is actually not a distance measuring device. Bluetooth is a way of talking. So what the apps do is people are asking, do they need to run constantly? Well, there's a magic of Bluetooth. The magic of the way Bluetooth was designed is that if you have a Bluetooth, it's always at a very, very low energy, listening to see if someone's trying to contact it. Think of it like your Bluetooth headphones. You can suddenly pair them, right? Or if you start to pair them, it's like somehow, okay, I don't exactly know how Bluetooth headphones work because I don't have Bluetooth headphones. You do have to put them in pairing mode, but that pairing mode happens to also be because you don't want to be randomly pairing lots of people's headphones. But we managed to do it in a way so that it wouldn't actually eat a lot of battery life. And in fact, I have it running on my phone all the time, and it doesn't eat, it's basically not noticeable. And what if Bluetooth is off? Unfortunately, then the device doesn't work. You need to have the things on in order for it to work. But what happened is with the Bluetooth, if they are nearby, one of them asks the other, hey, can you play the sound? And then microphone opens, speaker opens, sound goes across, and microphone closes. And then we analyze the sound to go and find out how long it took for the sound to get there. So that's actually how the system works. We use the speed of sound and we transmit. Now you might say, well, that's trivial. Why doesn't everyone do that? You see, it sounds obvious. Everyone should do this. It's so obvious. Like that's how we do it with lightning, right? Well, here's why it's hard. And here's the math part. And this is like, at this point, I'm going to go into something which maybe will make most sense only to high school students. But I want to maybe talk about this a bit. It's cool. So, okay, we're going to use sound. What does that mean? I need to know the speed of sound. Does anyone know how fast sound travels? This is actually very important. Somebody type into the chat. What's the speed of sound approximately? Mach 2. No, it's Mach 1. But it's like, it's like 340 meters per second. I'm going to do it in our American units. Speed of sound in American units is 1 foot per millisecond. Now, there's a reason I wrote it this way. If you're doing contact tracing, it's important to know whether I was 1 foot away, 3 feet away, 4 feet away, 6 feet away. This is useful for me. But if I'm, oh, just a second. my computer just flipped in a funny way, but I'm back. Okay, right. But if I'm like 12 feet away, it's not as important. If I'm 50 feet away, it's not important. What I'm trying to say is that, oh, doesn't it travel faster in moist air? You're right. But I'm going to say, look, what we care about in contact tracing is, were you less than 6 feet apart or were you more than 6 feet apart? Does that make sense? And if you go and take the speed of sound into effect, it's like, look, if you were 5.3 feet apart, it's like still less than 6 feet apart-ish. Actually, the way we make our app, we detect whether you're 9 feet apart. And the reason is because if your noses are 6 feet apart, your phones might be 9 feet apart because you have arms, okay? Do you think we can convince enough people? We'll get to that soon, okay? But first, let me talk about like the math behind this. So now sound is like about 1 foot per millisecond, and this is showing how hard the problem is. So I now need to detect my distance, and I'd like my distance measurement to be correct up to plus or minus 1 foot. Does this make sense to people? If I tell you, hey, you know, you were 4 feet apart plus or minus 20 feet, is this useful? No. I mean, like the 20 feet thing is like, hello, I can't tell the difference whether you were close or far. But it's also not very important to say you were 6 feet 2 inches plus or minus 0.1 inches. You don't need that, right? All you need is like about like a foot of accuracy is what I need. Once you look at this, you're like, oh, then my sound timing needs to be about 1 millisecond. I need to be able to say, hey, the sound was made and it went over and it got to me and it took about a millisecond. Sorry, not a millisecond. It took about 3 milliseconds, right? But I need to measure my time in like plus or minus 1 millisecond error. Okay, now here's where it gets hard. How long is the sound pulse that you make? Does anyone know what a 1 millisecond sound pulse sounds like? You know, like if I wanted to make a sound pulse, one way to make sure I can measure like, oh yeah, that's the millisecond that it came, is because if the sound pulse is just 1 millisecond long, then you're like, blip, it's there. 1 millisecond is like, it's imperceptible. You won't get it. It will be too quick. You couldn't even tell if it was just that somebody went bam. You know, like, what is that? You need to play a sound for longer. In fact, the sound length might be tens or even hundreds of milliseconds. Here's why it's hard now. Suppose you're just going to make a sound where you go like, ah, for like a millisecond. Then exactly which millisecond did it start in? Do you see why this is not trivial anymore? It's like if you're going to make a sound which is hundreds of milliseconds, well, like 100 milliseconds long, and you need to figure out exactly when it started, that's hard. And the reason why it's also hard is because if you're indoors, there's geometry. Sound travels and bounces off the ceilings and off the floors and off the walls. So actually what you get if you play a sound pulse for 100 milliseconds is mathematically, you're adding together multiple functions. This is again the high schoolish part, right? So I'm adding together a bunch of superpositions of delayed sound waves. Does that make sense? Like there's the one that's heard directly, and then there's like the reflection off the ceiling, which is slightly lower amplitude, but the way that sound works is you add the functions. So now I have all of these superimposed sound waves, and I have a lump. It's like somehow, what did I end up getting? If I transmit my sound, then maybe this is time. And what I actually get from my sound waves is like not much going on, and then suddenly like, whoa, something happened, and then it went down, right? And maybe this is 100 milliseconds. MS is milliseconds. How in the world do you figure out where it starts? That's actually hard. How in the world do you figure out where it starts? So there are some secrets that we do. Which I can't exactly say here because we're not public about those yet. We'll go completely public about those as soon as Novid takes off. But right now, the reason why people pay attention to us is because we're the only people in the world who managed to crack that problem of being able to tell exactly when it started, even though you've got this big fuzzy 100 milliseconds. By the way, with the big fuzzy thing, if you just told someone it started around there, plus or minus 50 milliseconds, you'd be telling them your distance up to plus or minus 50 feet, right? So, oh, and yeah, you can send the other device a designated time to start. You see, even if there's a designated time to start, what I'm emphasizing is that on the receiving end, on your microphone, it's very hard for you to know exactly when you started getting the sound pulse coming in. This is the magic of what's called Fourier analysis. Fourier analysis is how you analyze sound waves. I mean, Fourier analysis is a beautiful area of mathematics. When I first learned it as a college student, I was like, when am I ever going to use this? I didn't know. It was just neat math. But it turns out that it was extremely helpful because we actually don't just make a sound wave that goes like, ah. It's not just like one sound. We play a very complicated thing in order to have good properties here. don't you need super accurate clocks? Well, actually, oh, I love that question. The reason why I knew this would be possible is because I knew that there were clocks in your phones that make GPS work. And I was like, look, if your GPS works, GPS is done by satellites making pings at very specific times according to atomic clocks with extreme accuracy. And based on the time it takes for that ping to get to your phone, that time times the speed of light lets you triangulate your position on the surface of the Earth. And what I said is, look, if we can find from GPS 5-meter accuracy from light, which travels at 300 million meters per second, then I can definitely track something that travels at only 300 meters per second, because the phone has something which is accurate enough to track 1,000,000 times faster. So that was part of the thought process of why we knew this would work. Okay, and let me just give you one tidbit of Fourier analysis, which is fun. One thing that we do is also to find out whether two devices are in the same room. You may or may not have heard that people are starting to talk about COVID as something that doesn't only transmit within 6 feet. It actually also might transmit if you're in the same room as someone for a long period of time, because the particles stay in the air. This is not confirmed yet, but people are thinking that might be the case. So we have another part of ours, which even when you can't find out exactly how far apart the other person is, maybe because it's like very, very muffled, we can at least find out if you were around. And that's where the Fourier analysis comes in. I'll just share one little bit of that, which is, let's suppose that what's going on is like not much, and then suddenly it's like, wow, beautiful sine wave for a while, and then back to here. Okay, suppose that's the signal you see, and suppose that sine wave, this is time t, suppose that sine wave happens to be something like sine 3t. I'm just giving an example. Suppose it's sine 3t right there, and the rest of it, suppose it's like nothing and then nothing. There's a good way to find out whether or not this happens to match the frequency of sine 3t. Frequency means like, you may have heard of like radios transmitting on different frequencies. Frequency is to see whether or not I match. This is something like, this is like specialized radar pulses. Actually, what we're doing is something like that. We're making a specialized radar pulse, but I'm showing you how to think about sines and cosines with just a normal pulse. It's related to walkie-talkies. It's like you choose your frequency. And here's a way to find out whether or not there's something else at this frequency. The way to find out is, suppose you had a function. Suppose this was f of t. And suppose f of t is usually nothing, but over here, it's sine 3t. There's something nice that happens. If you take f of t, and if you multiply it by sine of 3t, then what you end up picking up is you actually end up picking up a very interesting function. Let me make my life a little bit easier, okay? Let me not have the empty stuff before. Let's just have sine 3t all the way. And this thing is robust to if I don't have it all the way, it still works. But just for the sake of argument, let's do it this way. If I do f of t times sine of 3t, well, f of t now is just sine of 3t. That's sine squared of 3t. I apologize at this point for the elementary schoolers. I want to give a little bit that's fun for high school students. Suppose you have sine squared of 3t. The interesting thing to do is that this, by the way, is actually always positive. And so if you went and took an integral, f of t sine 3t, from 0 to some big thing, like some big time t, suppose you went out to there, then what you get here is you get something that is linear in t. So you just keep on picking up more and more and more integral. Actually, you could even work out what this is, but this is like a decent positive thing. You pick up a lot of integral. But you know what happens if you took the integral from 0 to t of f of t times sine 2t? This is where it's really interesting. And this is like a fun tidbit for anyone who took high school trigonometry and was asking, why in the world do I need to learn what is sine 3t times sine 2t? Now, at this point, you're getting into things that I sort of forgot. There's some product to sum formula. Is there anyone who's taken high school trigonometry who can help me out? Like over here, that's what I've got here, all right? Sine 3t times sine 2t, oh gosh, what is this? There's some cosine stuff, help. I don't exactly remember this off the top of my head. Is there a 1/2? I'm like, I know there's some formula, it's got a 1/2 in it. I think the cosine one has a minus in it. I need help, guys. What is this thing? This thing is something you learn in high school trig class. Oh my gosh, people on this thing have taken high school trig class. It's like, what is this? There's a cos of a cos and a cos, right? Is it a cos something minus a cos something? Help. Okay, so it's like, yeah, it's like cos of the difference and then cos of the sum, okay? Cos of the difference is 3t minus 2t, and the sum is 3t plus 2t. Okay, whenever I look at this, I just back it out. I'm like, okay, I do know the cos formula. Cos 3t, cos 2t, cos 3t plus 2t is cos 3t, cos 2t. Yeah, cos 3t, cos 2t minus sine 3t, sine 2t, I think. That's right. Yeah, good. And it works, it works, it works. Okay, am I correct? Help me out. I think it's something like this. Please tell me if I'm right. That's what I need to know. Is it right? Okay, that looks good. Thank you. And now I'll tell you, when I was in high school and we learned this thing, I was like, what's it useful for besides homework problems? I don't know if anyone else had the same impression of like, the only thing this is good for is homework problems. And you got to memorize it, and there's like this half. Sometimes it's a half, sometimes it's a 2, sometimes it's a plus, sometimes it's a minus, sometimes it's a cos, sometimes it's a sine. Anyone else with me? Anyone else have this sort of impression? It's like, there's like all of these. It's like the sine, cos, the sine, sine, the what, and the whole page of nonsense. Now let me show you why it's critical. It's critical. Hey, what's this? Let's simplify. Half cos t minus cos 5t. You know what happens if you integrate that? Do you know what happens if you integrate cos? If you integrate this, it's like your integral will be like the integral of the half times the integral of cos t, and then you have the integral of cos 5t. Something really interesting happens. You get half. I apologize for elementary school kids. We're way beyond now, but I'm about to end the talk. This is cos, let's write it properly, cos t dt minus 1/2 integral 0 to t cos 5t dt. Oh, if you've never seen an integral before, all the integral means is like, it's the area under the curve. It's the area between the curve and the x-axis or the t-axis where the positives and negatives cancel, okay? But there's something interesting. If you have a legit cos t and it's doing this, you know what that integral does? It's basically 0. It's the wiggly thing. I mean, I think you mean the integral is the wiggly thing. But it's like somehow, if you do this, I have to say, actually, by the way, I meant to emphasize, I was just joking about this not being useful. This is incredibly useful. It's not only useful for what I'm doing here, it's useful in physics. I was just trying to explain that somehow a thing which looks like memorization is not just there for memorizing, it's actually fundamentally useful. It's useful in lots of places. And I just wanted to show this particular one as one way to see it. And also, this also is physics, right? But what happens, and I did not mean that to insult anyone who teaches this. I just wanted to give you another tool in your pocket of like, hey, here's a place you can use it. You can use it to find out whether a signal matches with another signal, okay? But now, if you do this, you know what happens if you integrate this? If you integrate something that's wiggly and periodic and it's like symmetric both above and below, this thing only fluctuates between like, I don't know, some number and some other number. I'm gonna just say it definitely is between -10 and 10. It's probably between like -1 and 1. But this is not much. It's just like flipping back and forth between some number and some other number. No matter what your capital T is, this thing here is just like, you know, it's kind of doing this. It's adding up and it's not much difference. Whereas if you did it against sine 3t, you get something that's linear in t. You just keep picking up stuff. That's actually how you can tell that the signal matches this and does not match that. So this thing here is constant. So this is bounded by constant. That's what we call it. Bounded by constant. Okay, so I'm just giving you a little bit of an idea of how you could tell the difference, right? Suppose that you were writing an app. That's actually what we were doing. You write an app. The app goes and takes the microphone recording. You can write an app that tells the difference between whether something is perfectly in a certain frequency or not. And the way you can tell is you integrate it actually not just against sine, but also cosine. There's a certain thing there. But you integrate against both of those, and then you can go and find out whether it matches a particular frequency or whether it doesn't match another one. All right, so that's just a little bit I wanted to share here. Actually, there's a ton of math inside all of what we did. Ultimately, with the complex exponential, well said. But what we do with this app is, I got involved in fighting COVID-19. I started to think, what can we do as mathematics to go and solve this problem? And what you see today is two mathematical ideas, which led to things that other people don't do. One of them was use the graph theory, and from the graph theory, go and figure out how far away the positive cases are, instead of just telling people, hey, you were directly around someone. Our real hope with this is to go and influence the amount of precaution that people take in the United States. And that will help us all survive this pandemic. The second piece was, let's actually construct that graph, construct those relationships correctly. And the way you do that is you don't use the Bluetooth, which is not sufficiently accurate. Instead, you use ultrasound, and you use some Fourier analysis like this to go and nail it down. So these are the things that we do. And actually, somebody was asking, how can you have people actually download this? Well, what we did is we found out that if you design something that delivers direct value, like showing you whether COVID is coming, we found out that people might actually want to download it. And so what we are currently doing is we're trying to talk to people who are in departments of health, but at the same time, we're also trying to talk to people at universities. We're trying to talk to people who do research in epidemiology or mathematics or medicine or any of these things, and maybe find this alternate angle that we put on interesting. We're trying to make this part of the national conversation. And if that happens, then we'll be able to bring more and more people into the system, just because the system actually provides direct value for anyone who's in it. All right. Well, thank you to everyone for listening to this part of the talk. I do want to leave a little bit of time to answer questions. I know we're over time by 7 minutes, but I see questions that came into here. I'm happy to start taking some of these here. I see people are all talking about other ways to do this. Yes, people are saying, what about near field communication, NFC? I should emphasize that the way that we are doing things with the entire app is that we see the smartphone as something which has lots of sensors, and we use every sensor for what it can do. My understanding is near field communication has too short of a range in order to be able to use. So that's why we didn't use it. On the other hand, we're happy to use math to go and do anything we can with the other sensors. And you're saying we could let people know at the testing centers. Yes, we'd love to. Honestly, if you guys have any ideas on how this thing can go out further, of course, we're happy to talk to you. And if there are any parents who happen to be watching who somehow have an interest in helping us connect to people, we're trying to do that. We're trying to save the United States right now. Right. So I see some other questions, which are, asking about the more traditional stuff that I normally talk about. How to prepare for contest math. I'll answer that question since you happen to have me, right? It's kind of funny that I'm here talking about COVID. That's not normally what I do. But if you want to think about contest math, here's what I'd say. Go and try to understand the ins and outs of everything. Yes, okay, you said contest because you want to do well on the contest. But if you understand why things are true, you'll also do better on contest math. As one example, this trigonometry thing I showed, don't memorize those formulas. It's best to understand how they come about. And that's also how I double checked it as soon as people said this formula. But also another thing is whenever you're going to try to do preparation for contests, go and try to do hard questions. You learn the most by doing things that you don't know how to do. I saw some people said I look bigger now. It's because actually I'm using a streaming setup, which I just zoomed in because now it's mainly me talking as opposed to me writing stuff, right? But if you want to learn how to do something, go and take on a challenge. And then when you go and take on a challenge, you will teach yourself so much. Actually, the stuff I'm talking about today, I didn't know about this, exactly the ins and outs of radar sensing. But in the process of doing the Fourier analysis and trying to make our own signals, I started to learn about what people actually do if they're trying to make radars and sonars. Very interesting. And other things that I learned how to do while doing this, I had never programmed an iPhone before or an Android device. I'd done normal programming, but I'd never done either of those. And so, well, got to learn, right? You just go and learn. And by doing so, I've learned by doing something that's hard. Somebody said Swift. Yes, that's what we write in the iOS app. But when you're talking about learning for contests, use the same thing. Go and find something that's a little bit out of your range, not too far out, but a little bit on the fringe of your range, and challenge yourself with it, and then that will work. I see that there were some people who said they shared with their teachers the fact that we have this Novid idea. Actually, we'd love to work with the teachers or the school district, because we also feel that if people want to go back to school safely, it's actually not a question of trying to control the spread in a school. It's very interesting. Because we've made this, a lot of people have come to talk to us. And whenever they talk to us, they say, I want to use your app so that as soon as the virus gets into my school or my university, then I'll be able to quickly control it. The first thing we tell them is, as a graph theorist, which is my specialty, I think that if your only control is after it got there, that might not be that great. It's best if you can also control it before it got in. And what we're trying to do is we're trying to talk to all of the school administrators, all of the university administrators. If they jump on, we actually don't just want them to have their students use it. We want them to go and say, hey, parents, everyone get on this. Let's build out a big defense, like a big defensive distance, so that as the virus starts to spread, you start to find out before it gets in. So anyway, if you're talking about schools, this is what we're looking for. You mentioned that students aren't allowed to turn on their phones in school. That's true. We've talked to a lot of schools, and we've even come up with other ways whereby if you're dropping off in a school, you might even be able to scan like a QR code, just being like, hey, I'm in this class now. And then that's it. Because the way our system works is we're just trying to build up that network. And if you build up that network, then you can tell people in advance. More questions. Wow, we've got lots of different comments here. Yes, people are saying it takes weeks for results to come back on tests. So actually, the reason why I got into this is because I was concerned that there aren't enough tests. I was concerned that in this country, we don't have enough tests going around and it takes too long for the results to come back. So in fact, what we're making is we're making this system which anonymously collects all this information. But then if you have one positive test, which is confirmed, we're actually going to add something where people can start to report symptoms like sense of smell being lost or COVID toe or all these other things. Those are not as firm signals as, ooh, it was a positive test. But if you actually on this network know that there's a bunch of really confirmed positive tests confirmed by the county or the health department, and then nearby them, there are these people who are showing symptoms, then suddenly you could actually alert people even before the test results get there. Does this make sense? It's actually a graph theory problem. It's like on my graph, we have all kinds of different labels of symptoms and times that things happened. And if you just go and use all this information together, then you could possibly even warn people before there are tests which are confirming positive cases. Okay, more questions. How important is it to be fast in problem solving? That's also a general question too. So I'll say, I don't think that you need to worry about whether you're the fastest in the room. There are many people who are not the fastest. I'm also not the fastest at problem solving. On the other hand, you can make up for that by fighting. So especially the story of what we're doing now, you just saw me tell you the story as of July 31st, 2020 of the state of Novid. Oh boy, we've had to work so hard because in order for us to get to where we are, we've been, doing things that trillion-dollar company has been trying to do. We've been doing things that national governments have been trying to do. They have a lot of speed too. But what we have is, I guess, hard work and time investment. And so I think what I want to encourage is, even if you feel slow, don't worry. You don't have to be the fastest in the world, but you have to want to do what you're doing, and then you can push it through. All right, more questions. Yeah, slow problem solving, don't worry about it. Don't worry about it. Don't think that you're dumb because you're slow. That's wrong. All right. How to avoid making silly mistakes? Oh, silly mistakes. Yeah, they happen. I would say that if you think of multiple ways to do every question, that helps. And I actually love thinking of multiple ways to do questions just because it's creative. And also, of course, it double checks the answer. And then if 2 ways got you the same answer, it's good. More questions. Somebody mentioned donations. Honestly, at this point, the thing that we're mainly looking for is not money. The thing we're looking for is that we find some way to let the whole world know that what everyone's been talking about with contact tracing has another angle using graph theory that could actually turn the whole situation around in the United States tomorrow. Like, that's actually what we're trying to do. Okay. Somebody asked, do you use multiple frequencies? Oh, yes, we do. And the reason we use multiple frequencies is because you could have a crowded room. And so you don't want all of the phones to be interfering with each other. So we do use multiple frequencies. And the frequencies we use are all in the ultrasonic range, which is 18.5 kilohertz to 19.5 kilohertz. The human range of hearing actually goes to 20 kilohertz when you're born, I think. But it very quickly loses sensitivity to those very top bits. Oh, somebody asked about the website XP for a second. Yes, we have a website. I mean, I'm actually, I don't know, I'm a funny guy. I'm a social entrepreneur. So I just do social entrepreneurship. I do things that I think are interesting. And about 6 years ago, I thought it would be interesting to make a free website for everyone to learn math and science with multiple different ways, 3, 2, 4, whatever, multiple different ways of learning any particular topic. And that's xp.com. If you actually Google various math terms, you basically land there. So we didn't make a website just to be like, hey, everyone, go to xp.com and that's your spot to learn. We just made something for which, as you go and try to do math, if you're Googling your topics, you'll often land on xp.com. And that's because we've given many ways to learn any subject. That's social entrepreneurship. It's a free website, teaches people math and science. And that's what I did first. And then, of course, what I do now, I spend most of my time now on Novid, but that's also social entrepreneurship. All right, more questions. Somebody is talking about a green shirt. Vote green shirt. What are you talking about? Must be somebody who used to be watching my live stream. So indeed, actually, clearly somebody knows that I was doing live streams. I used to do live streams every single afternoon at 4:00 p.m. Eastern time. I got busy in the last month, and especially with Novid picking up, unfortunately, the busyness has gone through the roof. But we are actually doing one today. It's not tomorrow, it's today. Today's Friday. Now I do the live streams like on Fridays only, 4:00 to 5:00. So actually, if you want, I guess I should say that. At 4:00, which is in less than 2 hours, I'll go onto a YouTube channel. It's free, it's completely free. And it's my YouTube channel. If you go to poshenloh.com/live, you'll be able to see how to get in. But what that is it's called Ask Math Anything. And people just ask random math questions, and I attempt to answer them. So that's just what I do for the community at this point every week. And that's why these people are talking about this green shirt. Everyone seems to want me to wear a green shirt, because if you have figured out by now, the system I'm using is not that normal. The system I'm using is actually a studio, and the studio happens to be a green screen studio, which you can tell if I start waving really fast. You can see the green behind my fingers. Anyway. So they want me to wear a green shirt so I disappear. All right, what is the YouTube channel for the live stream called? It doesn't really have a name, but if you just go to poshenloh.com/live, you'll find it. And poshenloh.com is that's my name. If you Google my name on Google, oh my gosh. I said if you Google my name on Google, that's so funny. That means Google is the verb too. But anyway, if you Google my name, you'll find my website and then go to /live. All right, other questions? Oh, should you turn on Wi-Fi background mode on Novid? Thank you very much for asking. Actually, there's a new mode on Novid that's about to go out. It's because iPhones are built so that you can't run things in the background at all times. So on Android, Novid is perfect. No matter what, even if the thing is, if the Novid is not on the screen, it just works. But on iPhones, if you want the full ultrasonic accuracy, you need to have the phone actually with the standby mode on. And that turned out to be too much complication for a lot of people. So we put another piece in that uses the Wi-Fi station that you're connected to, your Wi-Fi router, to indicate whether or not two devices are near each other. That one, what we do there is we say, if two devices have connected to the same Wi-Fi for at least like 3 or 4 hours, then we decide these are probably people who are close together in that relationship graph. This is not as accurate as the ultrasound, where we say, oh, you were within 9 feet for 15 minutes. We know it's accurate, so we're going to say that you were around each other. For Wi-Fi, if you use the background Wi-Fi mode, you need 3 hours. But that's still enough, because if these relationships that I'm trying to locate are you live with someone, you work in the same office as someone, you go to the same class as someone for like extended period of time, then at that point, the Wi-Fi works. So this Wi-Fi background mode is actually about to go out in the next version. Actually, my life is such that I do these math things and then I do the Novid things. And we're about to package up a new version to send to Apple, hopefully today. All right, let's take one more general question. And then unfortunately, I need to go and do something else. So let's see, what can we do here? Ah, yes, I like this one. This is about, do you need to have a certain amount of people to sign up for Novid in order for the accuracy to be high enough? So the way we see it is that there are two hurdles. One is the app, is anyone using the app? Is it giving me any information? For that, all you need is that everyone who has the app has at least 2 people they spend time with who also have the app. And each of those needs to have 2 other people they spend time with who have the app. And each of those needs to have at least 2 other people. You see where this is going. It's exponential blow up. Because on the app, we have a display that says, here's how many people in your network have the app. Now, how much does it take to get the 2, 2, 2, 2? We estimate that's like, if 10% or 20% of your people is good. Yes, okay. Don't you just need bigger than 1? Yes, to this audience, to this New York Math Circle audience, I can say just bigger than 1 is enough. You're right. But the way I usually explain this to non-math students or non-math loving students is 2, because everyone understands 2 people. Because if you told them, hey, all you need is at least 1.1 people have it, they'll be like, I know what 1 person is. How do I get a 0.1 person? Do you know what I mean? It's not like, yep, I got 1.1 by having my brother and my kid's sister. No, baby sister. That's not 0.1. Do you know what I mean? So it just doesn't work. So I'm just saying like, yeah, 0.1 person is a dog. Oh, wow. Since you mentioned that, I will say, warning. I've heard, and this is not confirmed yet, but I've heard that people are concerned that cats can be a way that you spread COVID. You want to check, you should fact check that. Anyway, but now back to this thing about the 2, 2, 2, 2, 2, like the 2, 2, 2, 2, 2, that will give everyone the idea that it works. You've got a network. Now, is it going to be accurate? The accuracy issue is if you've got a positive case at distance 12, it could be that there's another path through the network of distance 8 that gets to that positive case, but you don't know because those people aren't on Novid. The way we see it is if you got that 10% adoption to get this like network connecting and everyone saying, wow, there are 100,000 people in my city who are on this, that will be enough to give the impetus for a lot more people to join. And if a lot more people join, at that point, then the percent who's using it goes up. What I'm saying is that if you just go and say, you need 60% for the app to do anything, then no one joins. But if at 10%, the app already shows you that, oh, there's people in it, and there's some signals far away. Maybe the distance away from me is not 100% accurate, but I'm still seeing some signals. It's already useful. In terms of how many actually need to have it in order for it to be accurate, that's dependent on the graph, and that's a good area of research. I actually haven't done that piece yet myself. I will say it will not be as high as what's required for others, though. The reason why this works even better is because the other methods of contact tracing apps only take the positive case and tell the people directly around it. That requires a lot more compliance. A lot more people have to have it, compared to if you have every positive case tell the tens of thousands of people that are at any distance. If you see the difference is that we give you more time. We give you more distance hops. And because of that, we leverage that piece to get more, to work better, even if you have less people using it. Okay, well, unfortunately, that takes, I guess, our session today with New York Math Circle to an end. Thank you to everyone for coming today. I hope that you had some amount of fun. And thank you to the organizers for organizing this.
Thank you, Po, for giving us this exciting and very important talk. And we're very happy to see you always. But this is particularly important, what you've been describing to us, and gives us a lot of food for thought. Thank you again.
Great. Thank you. Have a great day, everyone. Bye-bye. I'm going to pop off.